And thanks for inviting me. It's really great to be here. And so I hope I can live up to this overblown introduction, but thank you so much. Okay, so I want to talk about local computation algorithms, and let me start with the context. The context is, we always have to have this requisite big data slide, but I want to talk about inputs that are so big, they're so huge that you don't actually have time to look at all the input. Okay, so I've been talking about this for 20 years. So what's new? What's new is not only do we have large inputs and we don't have time to view all the input, the computation problems we're trying to solve are not just like output a number like 10, but they're actually some large kind of answer to a combinatorial optimization problem, or maybe you want a sorting problem, but actually the output of the computational problem is large as well. Okay, so we have large inputs, large outputs. What can you do? You can't write down you can't view all the input, you can't view all the output. What happens if you don't actually need to see the whole output? I mean, there's an output that's computed, but you just need parts of it, okay? And do you actually need to see the whole input in order to compute the parts of the output that you need? Okay, so that's the question we want to ask in this talk. And what I hope to convince you is there are some non-trivial settings in which you don't actually need to see the whole input. You can compute the parts of the output that you care about much faster than in sublinear time in particular. Okay? So actually, I mean, this is not a question that I'm claiming to have invented. You may have seen this type of question in other guises. So let me mention one kind of famous example. There's something called locally decodable codes. So here you think of the input is actually the encoding of an extremely long message. Okay? The output of the decoding algorithm is the original message. Okay, so now the question is, do I have to decode the whole message in order to find the ith bit? Maybe I don't really want to know the whole message. I just want to see it. I know it's like some sorted order thing, and I just want to see if my name is in there. So I just want to do binary search in this thing. I just need to look at log n bits of the message, and then I'd be all set. Do I have to decode the whole thing? And the answer is no, you don't have to. There's some really cool things called locally decodable codes, which allow you, they allow you to get almost the same rates as the regular coding system, but they also allow this local mechanism where if I just want the ith bit, I kind of pay a certain amount to get the ith bit, but not too much. And then if I want another bit, I can pay a little bit more for the next bit, but I don't have to decode the whole thing at once. And that's a little bit non-intuitive because you would think, okay, these error-correcting codes, they're so redundant that you sort of have to look at everything, and there's all these redundancy built in, that I probably have to look at everything in order to decode. And it turns out that's not true. Okay, so you can build really cool locally decodable code systems with pretty good rates. Analogously, local decompression. Again, what you would want from local decompression is you'd want a system that the input here is the compressed data, and you would like to decompress the parts of the data that you're interested in. Maybe you want to do binary search. Okay, so now what does it mean? The typical famous systems we have for compression are not locally decompressible. How do we make them decompressible? So that's the question. And the more relevant question is, can I make them locally decompressible and maintain the same compressibility? Okay, so we don't actually have theorems about how well Lempel-Ziv compresses. Actually, we do have theorems. We know that we have theorems. We have theorems that you can't, in general, compress. Okay, but what we can say is, let's say Lempel-Ziv may work well on certain types of data. I can now give you a local decompression system that does nearly as well as Lempel-Ziv, but also gives you this local decompressible access. Okay, so that's the kind of thing you could do. You could say, I'm competitive with a certain other famous compression system, and I give you, in addition, this local decompressibility. I want to mention there are some other examples, but there's another one I want to mention that a lot of people have done work on in various communities in mathematics and in kind of electrical engineering and information theory type groups of people. And this is and also within computer science, is to estimate the page rank without actually going and inverting a linear system and telling me the page ranks of all the pages in the system. I just want to estimate this page, and I want to look locally around. I don't want to figure out in the whole system what does the page rank work out to. Okay, so is that something I can do locally instead of globally? Figuring out things like communities. There's some problems people are interested in if you assume that your network was generated as a preferential attachment. Can you find the original page? You know, can you find the first page? So there's things that people have shown how to do this. I'm not putting all the citations here, but there's whole communities out there working on problems like this. Okay, so so it seems like maybe we should have some sort of model that allows us to unify these problems. Okay, so this is a model that we'll propose. Let's assume the input is written down somewhere. Okay, that's written down. It's really big. We don't have time to look at it, but it's written down. Okay, and what we have is random access to it. Okay, now there's some output that's supposed to be computed for that input. That is not written down. Nobody computed it yet, but it's kind of, it's imaginary. Now, what we'd like to do is write some kind of procedure, which we'll call like a local computation algorithm, and it kind of processes queries for us. So we query this local computation algorithm, and we ask it, what is the value of the output at location I1? And it may probe the input in a few places, do some computation on the probes that it looks at, and then say, oh, the answer is y sub I1. Okay? And then they say, okay, well now I want to know what's the value of the output at location I sub 2. This local computation algorithm will make more probes and give me the answer of y sub I sub 2. Y sub I sub 2. Okay. Okay, so that's the idea. Like, it's going to be a query processing thing. This guy should only, hopefully, look at sublinear amounts of the input, maybe constant, polylogarithmic, square root n, n to the 2/3, something less than linear. And it should be able at each point to give me an output. Okay? I'm going to use queries to talk about the queries to the local computation algorithm. And we'll use a different word. We'll use probes to refer to the local computation algorithm looking at the input. That's just to keep things separate. Okay? Okay, any questions on the model before I move on? Yeah. There were two of you guys. You guys fight it out. Okay.
Does the computation of y I sub 1 impact your ability to compute y I sub 2? Or are they unrelated computations?
That is such a good question that I'm going to not answer it. I mean, I am going to talk about it, but that's a really good question. And so I'm going to get to that in couple slides. Yeah.
So the running time of the local computation algorithm should also be less than the size of y. So let's say you can be sublinear probes, but running time that's enough to approximate y.
Right.
Then
That's a good, yeah, good point. Okay, so I guess I should say that in the examples I'm thinking of, the output y is going to be roughly the size of the input x.
okay.
So like input x might be a graph, and the output y would be at like maybe at least the number of nodes, because we'll talk about problems that I'll define in a minute, but things like graph problems like maximal independent set, vertex cover, things like that, where you need to say for each node whether it's in the maximal independent set or not. So it's going to be pretty big. So, right, so we are going to want this guy to be smaller than y, but that's true. We don't want it. That's one perfect way of saying we can't compute all of y. Okay, good. All right, so let's start with a running example. And let me just make sure that we're on the same page. I want to talk about maximal independent set. Here the input is a graph, and the queries that we're going to make to the output is we're going to ask this LCA, is node U in the maximal independent set? Okay, and it's going to say, oh yeah, U's in the maximal independent set. Then we'll ask, is node V in the maximal independent set? They'll say, no, V's not in the maximal independent set. Then we'll ask about V's neighbor, is he in the maximal independent set? And they'll say yes or no, or whatever the answer he decides to say is. Okay, so now I get to your question. Okay, So here's an algorithm that works. I mean, if you just, on the first node that you asked me about, if you asked me, is U in the maximal independent set? I might as well say yes, because it's, why not?
You're using a definite article for the independent set, but you really mean
Yes.
like a maximal independent set.
Yes,
Yeah, okay. You said
yes,
E earlier.
I did.
Yeah.
And yes, A. So this is great. Okay, good. So this is a key problem. That I'm saying A and V and A and V, and what am I talking about? Okay. Okay. So what is the problem? There is going to be a problem, and that is there are lots of maximal independent sets. The node U is in some maximal independent set. Is it in the maximal independent set? That depends what I mean by the. I need to have some notion of consistency. So I'm going to get to the consistency in a minute, but this is the main issue right now, okay? If I didn't worry about consistency among what, okay? So let's just take an example, and now I'm going to give you an algorithm that you were asking if my answer for V could depend on my answer for U. I'm going to give you an algorithm that lets things depend on previous choices, okay? And then we're going to see that that leads to a problem of a certain type with consistency, okay? So, yeah.
Just think of this, some students from my class,
Yeah.
and they give me a hard time a month ago about like using the word maximal and maximum.
Oh, thank you. Yeah. Yes, thank you.
I know what you mean.
No, thank you, because what I was supposed to say on this slide, but I forgot, because I got so excited about answering your question. Oh boy. Okay. The whole point of this slide was to focus on the fact that I'm talking about maximal, not maximum. Okay, so remember, maximum independent set is an NP-hard problem, finding the largest possible maximum independent set. Like the largest possible independent set, NP-hard. I'm not looking for the largest possible, I'm looking for a large one. And in particular, it may not even be that large, but it's going to be one that I can't improve by adding a node, okay? Any node that I add to the maximal independent set is going to be a neighbor of something that I've already put in. So maximal means I can't add any other node to my independent set and keep it independent, okay? But just to be clear what independent set is in case, independent set means that I have a set of nodes where no two of which have an edge between them. Okay, so if I have a maximal independent set, all the other nodes in the graph have an edge to somebody in my maximal independent set. So I can't add them in. Okay, great. Thank you for saying that. Okay, good. So this, by the way, is not NP-hard because the greedy algorithm works on it, which is why I'm suggesting the lazy greedy algorithm right now. The greedy algorithm says, okay, let's just keep adding the nodes, and if we can add it, just add it. You know? So let's say, is node U in the MIS? Well, if the neighbors of U haven't been put in the MIS yet, put U into the MIS. Why not? But then you have to remember the decision. Okay? So then, yes, this could affect the output. I mean, this will affect the output. Because now the neighbors can't be in the MIS. All right? So this is this is a possible thing, and this works. The space I need is order the degree. For right now, let me assume the degree is constant, so that's not so bad. Okay, so I have constants. I spend constant time looking at all my neighbors and seeing if I've put them in the MIS yet. I mean, maybe I have like order n local space, and I just keep a bit array saying who I put in the maximal independent set and who I didn't. My input tells me the graph, so in the input I look and see who's used neighbors. And then for each neighbor, I look in the bit array and see, did I put them in the maximal independent set or not? And then, you know, if none of them were put in, then I put you in the maximal independent set. I'm done. Order D time. Okay? Not so bad. But I got to remember the decision, so I have to keep this bit array of length order n. Okay. Well, so that probe complexity was order D, but I needed order n space to remember the past choices. And notice that my answer depends on the query order. Okay.
Use much less space unless you're, depending on how many questions you're asking, it's like you want log n times the number of queries you made already. If you use some database that's, you're really using speed, I guess. You want the bit array because of speed.
You're saying I could just keep track of, okay, right. So this could be order the number of queries that have been made so far. That's right, that's true.
Okay.
That's true. So order n is just because I'm not bounding the number of queries, but that's true. It's order the number of queries to remember past choices. Okay, and my answer will depend on the query order. Is that bad? Well, maybe it's not so bad that my answer depends on the query order, but I can't have non-interactive copies of the LCA algorithms running around. Okay, so like I can't be working, okay, and this is important. Why is this important? When you give a data structures exam for 350 students, which I did last year, okay, then you have a team of 15 TAs, and you're seating the students, and you don't want two students to sit next to each other, right? So you need an independent set. Is this right? So, and also you want so you want also to be able to access them. So you have this team of 15 TAs, and you've got this huge auditorium. All these people are streaming in, and everybody's trying, no, you can't sit there. Yes, you can sit there. No, you can't sit there. So we had to agree on a system in advance because we were independent copies of LCAs running around computing maximal independent sets. Okay, so just so you know, this is an incredibly practical problem. Don't just poo-poo these theoreticians. Okay, so that's why we didn't want that. So these are the problems we'd like to avoid. Okay, and the main challenge is consistency with a single solution. Okay, because what's the problem here? This gives you a very specific solution, and the solution was defined by the query order. If somebody else gets a different query order, they're going to give you a different maximal independent set. Okay, so that's the big problem.
Like you care which one, as long as you can grade them.
That's right.
Yeah.
That's exactly right. Okay, so the question is, how are we going to be able to agree on one? Okay, so here's the model. So I'm going to be a little bit more specific on the model. We have this input. It's RAM. The LCA gets a random string. And I didn't put this in the picture yet. But let's assume that if we had copies, I'll talk later, if we have copies of the LCA, let's say we can agree on random strings, okay? So like me and my TAs, let's all use this random string before we go off there. And we'll all use the same random string to figure out what we should do. Okay, so we each have some random string in some workspace. And as before, there's some output that is not written down. There may be lots of independent sets that are possible. Okay, but we toss that random string. That picks one of them. Okay, and now we always have to answer according to this guy. Okay, so we don't get to switch between the different independent sets. We have to stick to this one. Okay, so this is our consistency. What we'd like is that the time, the space, and the random bits all be sublinear, hopefully polylog. But we're not going to be able to do polylog all the time. I mean, that would be a great goal, but it's not going to always work. Okay? Okay, any questions? All right. So that would be, this is like if you had swarms of little LCAs. Who was that was working on bees? You were working on bees, right?
No,
Not yet. Okay, but the bees could agree on the random string, and they could run around and swarm around and compute their MIS. Okay. Okay, they just need to initially share this random string, and then they're all set. Okay, but I just want to point out about these bees. They don't talk in the middle. They're just in the beginning. They share that random string. That's it. That's the end of their communication. After that, they have to compute independently. Okay, how in the world are we going to design these things? Because it sounds too hard. Well, here's some hope. Like, I would want to find some kind of algorithm that is already out there that I can use somebody else's algorithm, where the answer that I would give for node V doesn't really depend on anybody else. You know, like they somehow made some kind of the dependency graph on the answers I would give for V. Maybe V's answer depended on W, and maybe that depended on Y, but not too many other people. But that seems really hard to find. Where would you find such algorithms where V's answer only depended on a few other answers, and those guys didn't in turn depend on anybody else, so I could just figure out their answers and then figure out V's answers, and I'm done. That would be amazing, but why would I even imagine such an algorithm existed? Okay, so the reason you can imagine is because there's these amazing thing called, in distributed algorithms, called local distributed algorithms, okay? And the thing about these algorithms is that they are so fast that actually the answer at any node of a distributed, okay, I got to tell you something about distributed algorithms that I didn't understand when I first looked at them. So they do things like compute. Okay, so I guess if you deal with parallel algorithms, there was a parallel architecture, and then they would get some input, and the input had nothing to do with the parallel architecture, right? You might work on a butterfly, or you might have a sequent. There were all these different parallel architectures. They had nothing to do with the input. In distributed computation, when they compute maximal independent set, they're doing it on their own graph. So the graph that they're computing an independent set on is on their own network interconnection graph. Okay, so their network interconnection graph is the input. Okay, so that's one thing to keep in mind. The other thing is they have had amazing strides in the last 10, 15 years on round complexity algorithms that are constant and really, really small. So they have amazing results, which I'm going to mention in a few minutes. Okay, but they can basically show that the answer at any node depends only on a very small neighborhood around it. So it's exactly what we wanted. Okay, it's exactly what we wanted, that my answer depends only on the inputs of some of my small neighborhood. Okay, and what Parnas and Ron showed is that if there's a k-round distributed algorithm for any problem, but in particular MIS, then what can we do? V's output is only going to depend on the k-radius ball around it. Okay, let's just do this for k equals 1 for a second. Okay, if there's a one-round distributed algorithm for MIS, which there isn't, but let's say there was, okay? What does that mean? It means in one round, I can send messages to my neighbors, and they can send messages to me. That's it. Okay? So if somebody gave me a one-round distributed algorithm, I could simulate it sequentially, like what happens for node V. I could say, oh, what's V's input? Then I could figure out what he sent the neighbors. And I could look at all the neighbors' inputs and figure out what messages they sent to V. Then I could figure out what computation V would have done on their messages and figure out what V would have output. And you promised me that that was a one-round distributed algorithm, so I know that I'm getting the right answer. Okay, because I'm just simulating an algorithm I know to be correct. And I'm telling you, we can simulate V's view of that thing in order D time. That's all I have to do. Okay, so I did k equals 1. There is no one-round algorithm for MIS, but there are small round algorithms for MIS, okay? So in general, for k rounds, what can I do? I can only get I only need to simulate what happens in the first round between me and my neighbor, basically this whole ball. I need to simulate what they all do in the first round. Then I need to simulate what the k-1 ball does in the second round, and the k-2 ball, what they do in the third round, until it comes down closer and closer. And then in the last round, I just need to simulate what my neighbors did. And then I can figure out what I would do, what messages they would have sent me and what I would get, okay? So in general, in D to the k probes, I can figure out all these inputs, and then I do the simulation. All right, so that's just D to the k. So what D is the degree of the graph. Let's assume constant for now. Let's just assume constant. K is the number of rounds of the distributed algorithm. So the whole game is finding distributed algorithms where k is constant or very small. And if we can do that, then we can sequentially figure out what V should do in D to the k time, which is hopefully really small. Okay? Is this clear? All right. So now the question is, how big should k be? Because I already told you one round isn't going to do it. Okay? All right. And here, what we want is like constant rounds, and there's fantastic progress in local distributed algorithms. Okay, so I didn't write their name on the slide, but there's the work of Kuhn, Mosky-Broda, and Wattenhofer, like a whole series of works, even things like, even things as general as all packing problems. These are LPs where everything is positive. That's how I like to think of it. It's like there's nothing going on that's negative in there. Okay, so their constraints are all less than or equal to's, and you're trying to maximize something subject to these less than or equal to constraints, and every one of the coefficients is positive. Okay, that's packing problems. They can do all packing problems. They can do all covering problems, which is sort of the dual of the packing problems. So they can't do all LPs, but they can do all of these things as long as they're sparse in some sense, which I'm not going to get into right now. Okay, so that's an example. They can do MIS, they can do this, they can do that. It's really amazing what they can do. Okay, so what about MIS? They can't, actually They can't do MIS. We're going to do MIS, okay? I mean, not just us, but a bunch of people are going to do MIS, but not that. Just remember, it's not so clear. Like the lexicographically first MIS is a p-complete problem, which means we don't think this can be done in parallel. And that definitely means it cannot be done in constant rounds distributed. Okay, but that's to find a specific lexicographically first MIS. However, there still is, I mean, there's hope. You know, there was in 1985, I think there was a log n round randomized algorithm for maximal independent set. That in itself doesn't help us because remember, remember on our, that gives us, if we try to sequentially simulate the log n ball around node V, we have to look at d to the c log n different nodes, which is, notice this is going to be super polynomial. So we would have done better with our linear time MIS algorithm. So that's itself not quite there, but with additional ideas and different algorithms, you can do a lot better. So even, for example, Barenboim-Menelkin had a big improvement in the MIS algorithm. Even that gives you something much better. I'm going to describe a little bit more about some other ideas that got used later on in a minute. But all of these algorithms are based on somehow taking ideas from distributed algorithms, simulating them sequentially to figure out what happens at a specific node, and then getting the answer, okay? And what's interesting here is that actually this paper is a distributed paper, but it talks about local, so it does not, okay. It gives immediately a local computation algorithm, both of those. This one took a different distributed algorithm and made a local computation algorithm out of it. Same with this one. But these two actually are showing that the two communities have started to work together in the sense that they have results in the paper about local computation algorithms. So this is the paper by Ghaffari and Soda 2016 that won the Best Paper Award. He gives better local computation algorithms as well as better distributed algorithms. So actually kind of the thought processes of the two communities have come together in some way, although, there's sort of a give and take in the ideas. Okay, so I want to say a bit more of something we do on top of this idea of simulating the radius k ball, okay? And that is, and to do that, I want to describe for you Luby's algorithm, which is slightly simplified. Okay, so I'm giving you a simpler version, and we're not going to run it to the end. Okay, so in this algorithm, I'm trying to find a maximal independent set. So how would I do this? Everybody start out, like, uncolor yourself, or just let's say everybody color themselves yellow. Okay, now what I'm going to do is flip a coin with probability 1 over twice my degree. Okay, so if I have d neighbors, I'm going to flip a coin with probability 1 over 2d. Okay, if I come up heads, now if it comes up heads, I'm going to color myself red. And then I check and see, red means I want to be in the maximal independent set. I volunteer. I check, did any of my neighbors volunteer? If none of them volunteered, it's safe for me to put myself in the maximal independent set. But if somebody volunteered, I'm going to back down. Okay, so just this is an example. Okay, these guys all volunteered, so they all back down, okay? But if this time this guy volunteered, none of his neighbors volunteered, he puts himself in the maximal independent set and takes out his neighbors. Okay, so all these guys get out. All right, so it turns out that this thing happens, if you figure out what's the probability. The probability I volunteer is 1 over 2d. I have d neighbors. Each one volunteers with probability 1 over 2d, so the probability none of them volunteer is 1 minus that. If you work this out, this is easy to see that it's 1 over 4d, at least. Okay, so with some certain constant, like we're thinking of d as a constant. So if d is a constant, then with some constant probability, I remove myself from the graph. Okay, so what's the global behavior that goes on here? It means every node here after order d rounds of Luby's algorithm is going to remove himself and his neighbors from the graph with constant probability. But that's not enough for us because it could be that like the left side of the graph is all gone and the right side of the graph is all there. And that would be bad because I'd still have huge areas that are untouched. What?
Could have more elements than that.
What could have
An
what?
untouched area is bad because the maximal independent set would have things in it and you don't have anything in it.
Right. So I have to grow out there. And it means I have to process that area more and more and more. So it means like I may have made some progress, but I need some way of saying that I made more progress. What actually you can show happens is that if you run order D rounds of Luby's algorithm, then you shatter the graph into small connected components. So what you can show is it's very unlikely that a large connected component would survive. And when I mean large, I mean larger than some polylogarithmic size. Okay? So after you do order D rounds, what remains, something will remain because you're only getting rid of a constant fraction. But what remains is likely to be a very small fraction. It's like polylog size. So what's good about that? It means that these guys, you can go and look at them sequentially. You don't need to use parallel algorithms anymore. You know, we shattered this graph in the first round using Luby's algorithm. We figured out what we could figure out. Whoever remains alive after that round, I can just go find these guys, who's still alive, and find my connected component. It's only logarithmically many people that I have to find. And then it's logarithmic size. I can just pick the lexicographically first maximal independent set. Whatever I want to do that works. So this is like nothing. Okay? So that's going to be the idea. Okay, so the thing that's a little bit complicated here to remember, though, is that, okay, I just described to you a combination of a distributed algorithm plus a sequential algorithm, and I said, oh, that solves the whole problem. Remember that Luby thing, that was the Luby algorithm. This is a distributed algorithm. We're simulating U's view of it, okay, sequentially. So that means that I have to, for a node, I have to look at its neighborhood, simulate what Luby's algorithm would have done in the whole neighborhood, and figure out if I would have picked myself or I would have picked my neighbor, and if I would be alive or dead at this point. Like, would I be in the maximal independent set? Would I be dead? Or would I still be alive? And so I have to do the whole simulation of the rounds of Luby's algorithm, and I'm only doing order D. Okay, so how many nodes are in my D radius ball? D to the D. So it's exponential in D. That's why we're assuming it's a constant. Okay? It's not so great, but it's exponential in D, but I can figure out whether I'm red, green, or yellow at this point by doing the sequential simulation of Luby's thing. In D to the D time, it's exponential, but it's exponential in hopefully what we think of as a constant. Okay, and then I figure out, okay, let's say I'm green, then I say, okay, I'm not in the maximal independent set. If I was red, I'd say, oh, I'm definitely in the maximal independent set. And if I'm yellow, I still have to do some computation. I have to find out who's in my connected component. So I have to do like a breadth first search. I have to find this guy. Is he alive? That guy has to do the D to the D computation and figure out if he's alive. And I might go to this neighbor, and this guy has to do the D to D computation and figures out he's green. So I go back, I do BFS, I find this whole thing. I find this whole thing. I only have to do BFS. Every time I take a BFS step, I have to do this D to the D computation to figure out if that new person is alive. But I only have to do polylogarithmic BFS steps. So it's going to be polylog times D to the D. Okay, so this is the algorithm, right? So this was the order D rounds variant of Luby's. We prove the live connected components are small. In order to prove that the live connected components are small, we used a variant of the Beck-like analysis for the Lovász local lemma. That's the algorithmic version of the Lovász local lemma. And we proved that it's, with high probability, it's very unlikely that large connected components remain. Okay, so that's, okay, good. So then this guy alive simulates V's local view. This guy, okay, so what do? This is a subroutine, the D to the D subroutine that figures out, according to Luby, whether V is alive, dead, or in the maximal independent set. Okay, so now what the LCA does is it calls this subroutine that's order D to the D time, figures out if V's output is determined. If it is determined, output that answer. Otherwise, find the live connected component via the BFS, calling alive on each new thing you see in the BFS. But you will only have to go to polylogarithmic places, because that will be the size of your connected component. And then, once you find your connected component, any arbitrary way of picking a maximal independence set there works. But you've just got to be consistent that if some other local computation algorithm is running, they should pick the same one for the same component. They're going to get the same component, so we just have to agree that whenever you see this component, this is what you do. Okay, so I would say use greedy on like the node names of the, use some fixed order on the node names and you'll be fine. Okay, so this idea of the shattering idea was later used and improved in these works that I mentioned earlier in distributed algorithms to give better distributed algorithms and better LCAs than this. So in fact, I will get to that in a minute. Okay, so
It's important that the random string is making sure that when you run the Luby algorithm making random choices, everybody's going to make the random choice for the basis of the same random string, so they'll get the
exactly, that's how I know what my neighbor would have done.
Right.
Right, exactly. So, this is something. The way I've described it to you right now, good point. The way I've described it to you right now is I need to send, what do we need to agree on before we start doing the Luby algorithm? I need to know every node's random bits, what we do in the Luby algorithm. That's a lot of random bits. It happens, okay, let me just tell you, don't worry about it because there's all these de-randomization techniques that cut down the number of random bits that you would need. In particular, if you're familiar with pairwise independence, you only need pairwise independent random bits. So you just need to give everybody a seed for the pairwise independent bit generator, and everybody'd be fine. But if that doesn't mean anything to you, then just trust me. There are really well-studied, known techniques, and it's a beautiful area. So I encourage you to learn about it if you didn't know about it before. But it's well known. Okay. And it's nothing even that fancy. Okay, so I just want to mention another technique, which is a completely different technique for generating an LCA for maximal independent set. And this is using sort of, it's an idea that started with Nguyen and Onak. And the idea here is to think about this greedy algorithm again. Like if we simulate sequential greedy, what does that say? It says run through the nodes in some order, okay? And put V in the maximal independent set if none of the neighbors are in the maximal independent set yet. So we said that this is fine, right? Well, now what the LCA should do is it should compute what would greedy do on you. How do I figure that out? I have to simulate the results of greedy for all adjacent edges of a lower ordering. So let's say I'm figuring out U here, and its order is 10. If it has a neighbor here that's 9, I have to figure out, was N9 put in the maximal independent set earlier or not? On the other hand, if there's 15 over here, this comes after me in the ordering, so I don't have to figure out what happened. Like greedy approaches U before it approaches this guy, so it's going to decide what to do here before it even thinks about this guy. Right? So I just need to know anybody previous to me, or node number 1, node number 2, node number 9, all these guys previous, I need to know what greedy would have done on them. So I need to recurse on them. Okay, so that's okay, but the problem is, okay, maybe 10 is connected to 9, and I recurse on 9, and 9 is connected to 8, and I recurse on 8, and 8 is connected to 7, and I keep working my way down. That could go on forever. I mean, these dependency chains can be incredibly long. And what's nice is what Nguyen and Onak showed is that most nodes are okay if you use a random ordering. Okay, so if you think of
No, it's actually the initial of the authors. In fact, the answer was yes, so you could
do that. Yes. You're the first person that noticed that. Thank you. That's really good. Yeah, so the answer is, yeah. So most, okay, good. So what they noticed, though, is that this is going to be fine. Actually, what you can show is that if you pick your ordering randomly, okay? So let's assume there was some, we all agreed on a random permutation of our names in advance, which is a lot of bits. But again, this can be handled, never mind how, but standard techniques, okay? This is, if we all knew that our order was random, you could show that most of these chains are really small. Okay?
But
And
some about log n.
what's that?
I think maybe log n because if I got, is it still constant degree? Are we still constant degree?
We're still constant degree.
So roughly, if I've got my neighbors and the neighbor that's closest to me is likely to be 1 over d closer to the origin. So I should drop off, I should get I should multiply the distance to the origin by 1 minus 1 over d every time I take an edge.
Okay.
Sounds like it should take about log n to get down to the bottom.
That's right, but you can actually, okay, good. But then, that's good thinking. But let me repeat that, okay? And let me do a little better, only because, so I'm just going to give a high-level idea for why this might be true. Okay, so basically what it's saying is, you know, if my neighbor, well, how big are my neighbors? If I only have d neighbors and I'm pretty high up there, then I kind of, okay, let's think if I start going, let's think about if I were just to follow my minimum size neighbor, just for a minute, okay? Even though that's not the thing that we'll do. Actually, I'm trying to think how to prove this one right now.
It seems the bad chain
Yeah.
is the maximum neighbor the largest number that's smaller than my number.
That's right, okay.
If I follow the chain of that's the...
Okay, I think I have a better way to say it then. Okay, I have d neighbors, right? So wherever I am, the next one is like, you know, they're likely to be fairly evenly spread. So this intuition that the next one down from, so whoever's above me is above me, but the next one down from me is going to be about 1 over d less than me. Let's say our ranks are kind of random numbers between 0 and 1, okay? So that means like kind of I expect to see one of my neighbors at around 1 over d, another one at around 2 over d, another one at around 3 over d. I'm really oversimplifying here, but let's just go with me. So, you know, let's say I'm at around I over d, so my next highest neighbor is going to be at around I minus 1 over d. Okay, so I expect to go down by not even a factor of 1 over d. I expect to go down by 1 over d at each step. So that's why I expect to actually go down to, after about d rounds, I expect to run out of smaller neighbors. Okay, so that's why this thing actually is something like d to the d. It's going to be like order d. Okay, now the only thing is we need a little more than most. So they have a nice elementary argument, which I like to teach because I can actually teach it. Because I can it's like easy. So this is fairly, we needed a bit more than most, so there was some argument based on something called Galton-Watson branching processes. Never mind if you don't know what that is, because it's not that important for us right now. But you can actually show this is true over all the dependency chains, not just for most nodes, but for all nodes, the dependency chains are short. And one thing you may be concerned about is whether you need a long random seed for this kind of notion, because everybody has to pick a random ranking. And the answer is it's actually good enough to have log n wise independence, so no, you don't need a lot of bits. Okay, so for those of you that are worried, this slide was supposed to make you less worried. For those of you that don't know what I'm talking about, let's talk about another slide. Okay, okay, so so how fast can LCAs for MIS be? It turns out that the best, and this is using a different distributed algorithm, in terms of n is log star of n, which is like really tiny in terms of n. And in terms of d, then Ghaffari gives this thing, which is quasi-poly in d. It's like d to the log d. Okay, so it's not quite polynomial in d, but it's quasi-poly. So that leaves us an open question: can you get polynomial in d dependence? Okay, and but I think it's just sort of a case in point. What I wanted to mention is that there have been LCAs for lots of other problems as well. Approximate maximum matching, bipartite weighted vertex cover. This one with the approximate maximum matching was used in the learning setting by Fagan, Mansour, and Shapiri because they were basically trying to simulate what an adversary would do, and they were trying to come up with these protocols that would do well in these adversarial settings in sort of, anyway, so I won't be able to explain that right now, but it was used actually in a learning setting, the existence of LCAs, to show that you could develop algorithms for such things. I wanted to mention, so these are a bunch of other problems, some of them on graphs, hypergraphs, even KCNF. Again, this is using sort of the Lovász local lemma type ideas, and it has been applied in general to local computation mechanism design by Hasidim et al. And online algorithms. For example, I want to figure out which bin my ball went into. Like I'm throwing balls into bins, and maybe I'm using the power of two choices kind of ideas. And I want to figure out which bin my ball went into without looking at all the preceding balls. Do I have to look at everybody that preceded me to figure out so I don't know if you're, or can I just figure it out? So it turns out that you can do things here. Okay, so this is a whole bunch of areas. All of these are polylog query and space complexity. How many more minutes? 0?
Yeah, I mean, but
5 to 10. Okay, so let me just mention another problem and say a little bit about this. Whatever takes 5 minutes. Okay, so I've now finished the polylog part of the talk, and we're moving into sublinear. Okay, so here's a problem I want to talk about on sparse connected subgraphs. We know we have sublinear time algorithms to estimate the size of the MST. So if I have a graph and I can estimate the size of the MST under certain conditions in sublinear time, but can I find an LCA for a small weight spanning tree? Okay, so this question, I just want to know, I don't want to know the weight of the MST. I want to know, is this edge in it? Is this in a particular MST? So that's the question, but we don't know how to answer it. Okay, so let's remove the weights and go for a simpler question. I just want to know, given edge UV, is it in the spanning tree? I just want to know, is it in a spanning tree? Forget minimum spanning tree. It's all unweighted now. I just want to know, is it in a spanning tree?
Analogous to the independent set problem.
Well, it's analogous, except we still have this problem of consistency with the same tree, but we have a bigger problem. Okay, so it seems like, okay, great, we can use independent set. No. Here is a bigger problem. All right, here are two graphs. In this, I have to say yes on every single edge. Every edge here is in a spanning tree. In this graph, somebody has to say no. Who's going to say no? How do I even know I'm supposed to say no unless I look all over here and I see that all the edges are there? How would I even realize I'm supposed to say no? So this shows actually that there's a linear lower bound for this problem. So this is something we cannot solve. So let's make it easier. Okay, so this is forget the weights. We're no weights. Okay? Okay, this requires omega n probe, so let's just try to sparsify a graph. I'll give you some extra edges. You're allowed to, add a few extra edges. I just want it sparsified, but keep the connectivity. Okay, so that's what's happening here. It's not just a spanning tree. It's a small spanning graph. Okay? Well, in fact, what I want is, for my small spanning graph, is I want to say yes on a set of edges of, any edge I say yes on better be an original edge from the graph. I'm not allowed to invent new edges, okay? But I'm allowed to say yes on 1 plus epsilon n many edges. I need n minus 1 for a spanning tree, so I get epsilon n more. And this thing better be connected. That's the goal, all right? And I can fail with a certain small probability, and that probability is delta. I can mess up either the connectivity or too many edges, but let's try not to do that. Delta's small, okay? All right, so is this new problem easy? Well, there's an omega square root n lower bound, and that's because in this graph, this guy better say yes. So if these are two degree d n node random graphs, and this is just a random graph of degree d, okay? So here, if I stuck in this edge between these two guys, this guy has to say yes. But I can't tell the difference between being this edge or being an edge in here. Okay, and because I can't tell the difference, it takes me root n time to figure this out. It turns out to be a distribution testing problem. And it turns out that that's something I can't tell. All right, so this has a root n lower bound. Okay, I'm going to show you, so there's a lot of open problems here still. I'm going to show you an upper bound that works for special class of graphs, and I'm going to mention some Maybe I won't show you an upper bound. I'm going to, okay. So I'm just going to mention a class of algorithms or an idea and when it might work and when it might not work, okay? And it's okay, so I'm going to mention something called the centers algorithm. And here's the general plan. This is what we want to do. We're going to, so first I'm going to describe to you a global algorithm, and then we're going to figure out how we could simulate it locally. So globally, what we want to do is we want to randomly pick something like, and let me just blow the punchline already and tell you, I want something like square root n random nodes. So every node picks itself with probability 1 over square root n, which means I get about square root n centers, maybe a little more, okay? So I'm going to pick some random centers, and these guys are going to claim for their team. Their teammates are the people that are closest to them. So if you're closer to me than you are to Andrew, you're in my team, okay? Varna's in Andrew's team. And that's how we're going to decide. So that's why I call it Voronoi cells, because it means the people closest to me are in my group. People closest to Andrew are in Andrew's group. Okay, so, and we're going to have square root n things like this. Now, what we're going to keep for our sparse graph is this. In our team here, we're just going to keep a tree that connects us, some kind of spanning tree that connects our team. Okay, so each of these square root n groups gets like something like square root n minus n, square root n edges to connect their team. And now we have to figure out how to connect our groups. Like, I don't want too many connections to Andrew's group. It's enough, I'm completely connected. He's completely connected. We just have to connect one person from my team and one person from his team. That's enough. Okay, so if we could do that, so what I want is few edges between pairs of components. And hopefully this, because square root n choose 2 is something like n. In fact, let's make it square root epsilon n choose 2. That ends up being epsilon n. So that gives me epsilon n edges connecting between teams. Okay, so we have a spanning tree over each component that's within the team connecting. That's total n edges, because it's a bunch of spanning trees on disjoint parts of the graph. And between pairs of components, it's just the number of components choose 2. We pick the number of centers so that this is less than epsilon n. Okay? But what's the problem? I need to simulate this thing locally. So if I'm a node and I'm asking, is my edge to my neighbor supposed to be in this spanning tree or not, we need to figure out whether we're on the same team. If we're on the same team, we need to know if this edge is part of our spanning tree. Or if we're on different teams, we need to know if this was one of the edges that we saved between our two teams. Okay, so that's the difficulty. And so one of the difficulties, and another difficulty is, in order to figure these things out, I need to see my whole component. So I better have these components be fairly evenly sized, right? I don't want different sizes. So everybody needs to figure out who their center is quickly. Everybody needs to know their whole component. That's the issues, okay? So it turns out for expanders, you can show that this can be done, okay? So let me just go right by this. We just talked about that, so that's great. All right, so when you have good expansion, you can simulate this locally in root n time. I was assuming here that our degree is constant, though. Okay, what about other graphs? There's a new result by Lenzen and Levy showing n to the 2/3 time, and this is probably the max degree over epsilon. So there's this really cool result that shows that you can get this. It also gives a sort of a type of spanner property, which I'll leave for later. But it shows that you can do this in n to the 2/3 time. There's still not clear whether the answer should be n to the 2/3 or root n. We have no idea. It's not clear what the dependence on the degree should be. But I think it's, for this reason, it's kind of surprising from many directions. What they did, do I have anything about that? No, I didn't. I'm just going to say that they took this idea of dividing into teams, but then because some of the teams had different sizes, they had to break it down into sub-teams. And they had to allow a few, not just one edge between every pair of teams, but sometimes more between every pair of sub-teams. They had to allow extra edges. But they had a way of still sparsifying it further. It's really clever for how they managed to do that. And they were able to cut down the number of edges. Okay, so that's this. I wanted to say for certain kinds of graphs you can do better, but I'm not going to say much about it. I just want to say there are special kinds of graphs that are the opposite of expanders, which you can do this for in much, much faster. Okay, they're graphs which are like planar graphs, graphs that don't contain, that have excluded minors. So they have a lot of structure. They happen to be really nice to work with, and you can do a whole lot better for them. Okay, I think I'm going to skip this. There's some new work on other kinds of spanners, I'll just say. And there's some kind of preliminary work on this topic that I am not going to talk about. But what I want to say is there's a lot of open questions in this area. It's a fairly new area that we've been looking at only in the last few years. But most of the work has happened in the last couple of years in this area. We had a workshop last year called Workshop on Local Algorithms, where we tried to bring people from the different areas of computer science, math, information theory, together to talk about these things. We're going to have another WOLA this summer, so stay tuned. We just started thinking about it, so we haven't had a date even. But there's lots of different types of problems. There's lots of open problems. There's lots of settings where you could use this. And I think that that's pretty much what I have to say about it. Okay, thanks.
So you mentioned like special graphs, like planar graphs in the context of the sparse spanner stuff. In terms of the first half for independent sets, matching stuff, is there work that's been tailored towards specific types of graphs?
Oh, that's a good question.
I know you were generally assuming a bound and max degree, like something like a planar will have a good average, a small average degree.
That's a good question because I would assume you could do better. I can't remember. There's the answer. I can't remember if anybody's thought about this and what would have been the issues. But I think it should be doable to do better. I mean, you almost always can do better on those graphs. So I don't remember why. I mean, we have partition oracles, so we even know who's in the same partition and who's not. I remember this question coming up, but I may be misremembering that and I don't remember why.
Maybe somewhere there's some possible following
What I believe is nothing's written down. So that is, I think that if somebody does something in that direction, then you could write it down and claim it. That's for sure. Because I think there's nothing written down. And anything else, and I don't even know of any plans to write anything down. Let's put it that way. Okay.
Sorry for all the questions.
No, that's good. I like it better that way.
Okay, well, thanks.
Thank you.